Assalamu alaikum friends. I am Taqdees Ahmad Siddiqui with Computer Graphics for Bachelor's in Computer Science course being offered by Virtual University, Government of Pakistan. Today is our 42nd lecture. Last time we started our discussion about some viewing and modeling transformations using OpenGL. We haven't finished yet, so we're going to continue where we left last time. Let's begin. Viewing and modeling transformations are related in OpenGL and are combined into a single model view matrix. One of the toughest problems that newcomers to computer graphics face is understanding the effects of combined three-dimensional transformations. As we've already seen, there are alternative ways to think about transformations. Do we want to move the camera in one direction or move the object in the opposite direction? This is what we need to develop a feel for. Naturally, it would not come overnight. We'll have to practice it, and then only we'll be able to master the idea that we are going to perceive in the three dimension what kind of view we want and what kind of transformations are going to give us that desired result. That does take some time, but definitely there are certain considerations that we would be learning over the period of time, that how we can achieve the same thing or the same effect using two or more different approaches. Like the one that we discussed last time, that was if we want to have a different view, should we move the camera away from our object or should we move the object away from the camera? But both would ultimately be resulting in the same view, the same type of output that we desire. So there are going to be multiple ways of achieving the same effect. When we go into the details, we'll find out. Each way of thinking about the transformations has advantages and disadvantages, but in some cases, one way is more naturally matching with the effect of the intended transformation. If we can find a natural approach for our particular application, it's easier to visualize the necessary transformations and then write the corresponding code to specify the matrix manipulations. The first part of this section discusses how to think about the transformations, and later some specific commands are presented that would be materializing our thoughts. For now, we use only the matrix manipulation commands that we have already seen. Finally, keep in mind that we must call GL matrix mode with GL model view as its argument prior to performing modeling or viewing transformations. So whenever we'll decide to perform some modeling transformations or viewing transformations, we must set our matrix accordingly. So the model view matrix must be set before we can start working with the transformations for modeling or for viewing. So in the first part, as we said earlier, we are going to discuss the thinking part, thinking about transformations, so that we are able to establish what we want to achieve, and then we'll worry about how we can achieve that. Let's start with a simple case of two transformations: a 45 degrees counterclockwise rotation about the origin around the z-axis and a translation down the x-axis. So this is what we are going to take as a test case. We are going to join or combine two transformations, rotation and translation. Suppose that the object that we are drawing is small compared to the translation, so that we can see the effect of the translation evidently, and that it's originally located at the origin. We're starting with two presumptions. One is that our object is at the origin. The second is the size of the object is smaller than the translation that we're going to perform, so that हमें वो transformation होती हुई नजर आ सके. We should be able to clearly see that the object has been translated along x-axis. If we rotate the object first and then translate it, the rotated object appears on the x-axis. If we translate it down the x-axis first and then rotate about the origin, the object is on the line y is equal to x, as is shown in the next figure. The order of transformations is important. We have stressed this earlier on as well when we were talking about transformations, three-dimensional transformations and 2D transformations. 3D ट्रांसफॉर्मेशंस के अंदर हमने स्पेसिफिकली एग्जांपल ये वाली ली भी थी कि अगर हम किसी भी ऑब्जेक्ट को ट्रांसलेट भी करना चाहते हैं और रोटेट भी करना चाहते हैं तो ऑर्डर ऑफ ट्रांसफॉर्मेशंस इज गोइंग टू बी वेरी वेरी इंपॉर्टेंट in determining what would be the output. In this case as well, अगर हमने x एक्सिस के along ट्रांसलेट करना है और origin के अबाउट रोटेट करना है और ऑब्जेक्ट ओरिजिनली origin पर ही पड़ा हुआ है तो स्टार्ट में अगर हम पहले रोटेट कर दें अबाउट द origin तो सिर्फ ऑब्जेक्ट की ओरिएंटेशन चेंज हो जाएगी एंड देन विल बी ट्रांसलेटिंग दैट चेंज्ड ओरिएंटेशन ऑब्जेक्ट along द x एक्सिस. सो हमारा ऑब्जेक्ट अल्टीमेटली x एक्सिस पर ही दिखाई देगा. दूसरी सूरत क्या होगी कि अगर हम इन्हीं दोनों ट्रांसफॉर्मेशंस का ऑर्डर चेंज कर दें, रोटेशन बाद में करें, ट्रांसलेशन पहले कर लें. द ऑब्जेक्ट वुड बी ट्रांसलेटेड अलोंग एक्स एक्सिस फर्स्ट और उसके बाद जब आप रोटेशन अबाउट द ऑरिजिन करने जाएंगे तो ऑब्जेक्ट वुड बी फार अवे फ्रॉम द ऑरिजिन, नॉट ऑन द ऑरिजिन. सो बीइंग फार अवे फ्रॉम द ऑरिजिन, व्हेन वील रोटेट इट बाय द स्पेसिफाइड एंगल, वी आर गोइंग टू हैव द ऑब्जेक्ट मूविंग इनटू दैट एक्स वाई प्लेन. Right? We are going to have it rotate around z axis. So z axis के around जो rotations होती हैं वो x y plane में होती हैं. Therefore, ultimately the object would be poised at some point where x is equal to y. That would be falling along the line. But what we want would determine what should be done first. पहले translation करना है, उसके बाद rotation करना है, या पहले rotation करने के बाद translation करना है. Depending upon what we want, will be combining the two transformations in that very order, and that's where our thinking goes in. So we have to think about it first and then we decide what we shall be doing and how we shall be achieving it. In general, the order of transformations is critical. If we do transformation A and then perform transformation B, then we almost always get something different than if we do them in the opposite order. That is, we do transformation B first and then we do transformation A. Most often the two results are not going to be the same. Now look at this figure. This illustrates what we have been talking about. Rotation first or translation first is going to result in different results. Look at the left part of the figure. Here our object has been, it was originally on the origin. We have rotated it about the origin with the specified angle 45 degrees. And then that rotated object was translated along the x-axis. So ultimately what we get is the object poised at or along the x-axis at a different orientation now. But in the second part, right side of the figure shows that if we translate the object first, the object is translated as it is along the x-axis and followed by a rotation around the origin, and that would mean that we are going to rotate the object at the 45 degrees angle from its current position and rotating it with reference to the origin around the z-axis is going to result in the object poised somewhere up there in the xy plane, not on the x-axis. All viewing and modeling transformations are represented as 4x4 matrices. Each successive GL mult matrix or transformation command multiplies a new 4x4 matrix M by the current model view matrix C to yield CM. When we are talking about multiple transformations to be combined together, we would be performing these transformation operations successively. हर नई ट्रांसफॉर्मेशन के लिए जो मैट्रिक्स M है वो हम फ्रेम करेंगे, सेट करेंगे और फिर उसको जो करंट हमारा मैट्रिक्स है with the current number of transformations that we have performed reflected in there, उसके साथ हम उसे multiply कर लेंगे. This process would finish when we have done with all these transformations and now we want to perform these transformations on our vertices. So वो आखिरी स्टेप होगा जिसके अंदर हम इस मॉडल व्यू मैट्रिक्स को जो हमारे गिवन vertices हैं उनके ऊपर अप्लाई करेंगे and we'll get with our I coordinates. Finally, vertices V are multiplied by the current model view matrix. This process means that the last transformation command called in our program is actually the first one applied to the vertices, like CMV. By that time, we would have performed all multiple composite transformations that we wanted to perform in order, and then finally, having performed all those transformations, we would have come up with the model view matrix that we frame as a result of all those viewing and modeling transformations that are desired, and then those are applied in one go to our vertices. Thus, one way of looking at it is to say that we have to specify the matrices in the reverse order. Like many other things, however, once we have gotten used to thinking about this correctly, backward will seem like forward. Consider the following code sequence which draws a single point using 3 transformations. Look at the code. GL matrix mode, GL model view, GL load identity, GL mult matrix F n, GL mult matrix F of m, GL mult matrix F of L, GL begin, GL points, GL vertex 3F of V, GL end. In code, the model view matrix successively contains I, N, Nm, and finally NML, where I is the identity matrix. The transformed vertex is NMLV. The vertex transformation is carried out in the order N of M of LV. So V is multiplied by L, resulting in LV, which is multiplied by M, and the resulting MLV is then multiplied by N. So the order of multiplication would be that V and L would be multiplied together to form LV, and then multiplication of this resultant with M would be performed, and then the multiplication of that resultant MLV would be performed with N. Notice that the transformations to vertex V effectively occur in the opposite order than they were actually specified. Actually, only a single multiplication of a vertex by the model view matrix occurs. We have developed the basic understanding that this is the order in which evaluation would be taking place, but for all practical purposes, by the time vertex की बारी आती है कि उस पर आप model view matrix apply करें, तो model view matrix prepare हो चुका होता है, having gone through all those successive matrix multiplications that were required for the desired transformations. So vertices के ऊपर matrix multiplication का operation सिर्फ एक ही दफे हो रहा होगा. In this example, the N, M and L matrices are already multiplied into a single matrix before it is applied to the vertex V. Now let's talk about grand fixed coordinate system. This idea is going to be imperative in view of the example that we've already seen as well, the one that involved translation of object as well as rotation about the origin or around the z-axis. Thus, if we like to think in terms of a grand fixed coordinate system, we have to think of the multiplications as occurring in the opposite order from how they appear in the code. Using the simple example shown in the left half of the figure 4, a rotation about the origin and a translation along the x-axis, if we want the object to appear on the axis after the operations, the rotation must occur first, followed by the translation. To do this, we'll need to reverse the order of operations. So the code looks something like this, where R is the rotation matrix and T is the translation matrix. GL matrix mode, GL model view, GL load identity, GL mult matrix F T, GL mult matrix F R, and then draw the object. Let's discuss a slightly different idea, and that of moving a local coordinate system. Another way to view matrix multiplications is to forget the grand fixed coordinate system in which our model is transformed, and instead imagine that a local coordinate system is tied to the object that we are drawing. All the operations occur relative to this changing coordinate system. In the fixed grand coordinate system, we have the coordinate system fixed, and all other things in there are going to have their relative positions defined. But this new idea of local coordinate systems says that we associate a coordinate system with the object itself, the one that we are trying to transform, translate and rotate. अगर इसके साथ एक अपना इसका कोऑर्डिनेट सिस्टम, लोकल कोऑर्डिनेट सिस्टम एसोसिएट कर दिया जाए, तो फिर हम ये कर रहे होंगे कि जब ऑब्जेक्ट को ट्रांसलेट करेंगे तो उसको उसके अपने लोकल कोऑर्डिनेट सिस्टम समेत ट्रांसलेट कर रहे होंगे, और उसके बाद फिर ऐसा मुमकिन होगा कि हम स्पेसिफाई कर सकें कि हमने उसके बाद जो रोटेशन करनी है ऑब्जेक्ट की वो अबाउट द फिक्स्ड और द ग्रैंड कोऑर्डिनेट सिस्टम के ओरिजिन के अबाउट करनी है या उस ऑब्जेक्ट के लोकल कोऑर्डिनेट सिस्टम के हवाले से करनी है, एंड दैट कुड अर्न अस द वेरी ईज ऑफ ऑपरेशंस दैट वुड मिनिमाइज द अमाउंट ऑफ थिंकिंग रिक्वायर्ड. इससे पहले हमने ये कहा ना कि हमें सोचना पड़ेगा कि हमारा ऑब्जेक्ट जो है अल्टीमेटली आफ्टर ट्रांसलेटिंग एंड रोटेटिंग उसने अपेयर कहाँ होना है. अगर तो हम उसे एक्स एक्सिस पर ही चाहते हैं तो फिर हम अकॉर्डिंगली परफॉर्म करें अपनी ट्रांसफॉर्मेशंस, ताकि रोटेशन अबाउट द ओरिजिन हो जाए और फिर ट्रांसलेशन हो रही हो. ऐसा ना हो कि हम ऑर्डर इस तरह स्पेसिफाई कर दें कि ट्रांसलेशन पहले हो जाए और उसके बाद जब रोटेशन हो तो फिर ऑब्जेक्ट हमारी डिजायर्ड लोकेशन पर अपेयर ना हो रहा हो बल्कि उसकी जगह चेंज हो जाए. अब इस प्रॉब्लम को हम सॉल्व इस तरह से करने जा रहे हैं कि एक ऑब्जेक्ट का अपना लोकल कोऑर्डिनेट सिस्टम भी इंट्रोड्यूस कर रहे हैं. विद दिस अप्रोच the matrix multiplications now appear in the natural order in the code. To see this in the translation rotation example, begin by visualizing the object with a coordinate system tied to it. Of course, this would be a local coordinate system to that object. The translation operation moves the object and its coordinate system down the x-axis. Then the rotation occurs about the now translated origin. So the object rotates in place in its position on the axis. So what we wanted to achieve has been achieved because of that local coordinate system. हमने जिस origin के around या जिसकी respect से object को rotate करना था वो हमने उसका local coordinate system का origin ले लिया, और इस तरह से translation पहले करने के बाद जब हमने rotation perform की तो rotation हमने अपने grand coordinate system के origin के reference से नहीं की बल्कि object के लोकल कोऑर्डिनेट सिस्टम के रेफरेंस से की, जिसके बारे में हमने कहा कि हम उसको प्रिज्यूम कर रहे हैं कि वो हमारे इस ऑब्जेक्ट के साथ टाइड अप है. दिस अप्रोच इज व्हाट वी शुड यूज फॉर एप्लीकेशंस सच एज द आर्टिकुलेटेड रोबोट आर्म्स वेयर देयर आर जॉइंट्स एट द शोल्डर, एट द एल्बो एंड रिस्ट एंड सो ऑन अप टू द फिंगर्स. To figure out where the tips of the fingers go relative to the body, we would like to start at the shoulder, go down to the elbow and then the wrist, and so on, applying the appropriate rotations and translations at each joint. Thinking about it in reverse would be far more confusing. This second approach can be problematic, however, in cases where the scaling occurs, and especially so when the scaling is non-uniform. Scaling में क्या करते हैं हम? ऑब्जेक्ट की डायमेंशंस के साथ खेल रहे होते हैं, उसकी विड्थ को बढ़ा रहे होते हैं या उसकी हाइट को बढ़ा रहे होते हैं या घटा रहे होते हैं. सो अगर तो यूनिफॉर्म स्केलिंग हो रही हो तो उस सूरत में तो ये होता है कि हमारा ऑब्जेक्ट जो है वो तमाम डायमेंशंस में यूनिफॉर्मली स्केल होता है, एनलार्ज हो रहा होता है या श्रिंक हो रहा होता है. लेकिन अगर नॉन यूनिफॉर्म हो स्केलिंग तो उसका मतलब यह है कि मुमकिन है हमारी हाइट जो है वो कम हो रही हो और उसकी निस्बत हम अपनी विड्थ को मजीद बढ़ा रहे हों. इस सूरत में जो हमारा लोकल कोऑर्डिनेट सिस्टम वाला आइडिया है दैट हैज़ सर्टेन कॉम्प्लिकेशंस एसोसिएटेड विद इट. आपको याद होगा कि जब हमने स्केलिंग की बात की थी तो हमने कहा था कि जब हम स्केल करते हैं किसी भी ऑब्जेक्ट को विद रेफरेंस टू द ऑरिजिन तो रिलेटिवली उसकी पोजीशन भी डिस्प्लेस होती है. ऑब्जेक्ट को जब स्केल किया जाता है तो विद रेफरेंस टू और विद रिलेशन टू द ऑरिजिन, कोऑर्डिनेट ऑरिजिन, पोजीशन ऑफ दैट ऑब्जेक्ट इज आल्सो ऑल्टर्ड. वो डिस्प्लेसमेंट जो कि ट्रांसलेशन की शक्ल में दिखाई दे रही होती है इफेक्टिवली, वो किसके रेफरेंस से की जाए? फिक्स्ड वाले ग्लोबल कोऑर्डिनेट सिस्टम के ऑरिजिन के रेफरेंस से या ऑब्जेक्ट के साथ एसोसिएटेड लोकल कोऑर्डिनेट सिस्टम के रेफरेंस से. दैट can end up adding to some complexity of processing. After uniform scaling, translations move a vertex by a multiple of what they did before, since the coordinate system is stretched. Non-uniform scaling mixed with rotations may make the axis of the local coordinate system non-perpendicular, and that is where we are going to have complexity getting introduced. As mentioned earlier, we normally issue viewing transformation commands in our program before any modeling transformations. This way, a vertex in a model is first transformed into the desired orientation and then transformed by the viewing operation. We have talked about this earlier on as well, that wherever we are going to perform the modeling and viewing transformations, we should have this specific order maintained. Otherwise, we may have problems. The viewing transformations have to be specified prior to the modeling transformations. Since the matrix multiplications must be specified in reverse order, the viewing commands need to come first. Note, however, we do not need to specify either viewing or modeling transformations if we are satisfied with the default conditions. So it's not necessary that we would always be playing with it. If the prevailing conditions are satisfying, the required output is being generated, fine, we are comfortable with it. We don't need to exert. If there is no viewing transformation, the camera is left in the default position at the origin, pointing towards the negative z-axis. If there is no modeling transformation, the model isn't moved, and it retains its specified position or orientation and size. So it's not necessary that we would always be making use of a model view matrix. If the requirements are sufficed by our default values, जहाँ कैमरा डिफ़ॉल्ट में पड़ा हुआ है हमारे लिए अच्छा है, हम वहीं से देखना चाहते हैं, हम कैमरे को ओरिजिन से नहीं हिलाना चाहते, and we want it to look down the z-axis, fine, we should leave it as it is. And if we are not going to introduce any modeling transformations, of course the object would stay where it is, the very way with the very orientation and the very size. So वही अगर हमें required है, we don't need to specify it. But if we specify, of course this would be applied first in order to come up with the I coordinates, which would go into the next step. Since the commands for performing modeling transformations can be used to perform viewing transformations as well, modeling transformations are discussed first, even if viewing transformations are actually issued first. So regardless of their order, we are going to talk about the modeling transformations first. Makes sense? What object, in what form, in what size, at what orientation do we want to have, and then which way we want to look at it. So all those things are making sense in natural order. Often programmers write all the code which involves transformations to position and orient objects correctly relative to each other. Next, they decide where they want the viewpoint to be relative to the scene, and then they write the viewing transformations accordingly. So the actual order of thinking is also matching this, that you think about what objects you want in the scene, what size, what dimensions, what orientation you want to have, and then how do you want to view them, and then you perform the transformations accordingly. Having done this, having done with this story making, the way things are going to happen, the steps that are going to take place, then you actually take those steps. We're going to talk about modeling transformations first, as we have just discussed. The three OpenGL routines for modeling transformations are GL translate, GL rotate, and GL scale. As we might suspect, these routines transform an object or a coordinate system, if we are thinking of it that way, by moving, rotating, stretching, shrinking, or reflecting it. Can you recall when we talked about the reflection? Reflection can always be specified making use of the same matrix that we used for scaling. So that is why only these three routines, translate, rotate, and scale, they suffice for all our requirements. All three commands are equivalent to producing an appropriate translation, rotation, or scaling matrix, and then calling GL mult matrix with that matrix as the argument. However, these three routines might be faster than using the GL mult matrix. The idea is that if we want, we can frame our matrices the way we want them, set them up, and then call the GL mult matrix routine to get them multiplied together. But all those things, if they are performed making use of one of the three routines appropriately, the GL rotate, GL translate, or GL scale, these routines are more efficient. They behave more efficiently, they perform the work more efficiently than physically setting up the matrices and then calling the GL mult matrix routine to multiply them. So it is always preferable to make use of these built-in routines, GL rotate, GL translate, and GL scale. OpenGL automatically computes the matrices for us. In the command summaries that follow, each matrix multiplication is described in terms of what it does to the vertices of a geometric object using the fixed coordinate system approach. First we start with translate. Void GL translate, its variation can be with F and with D. So we can have GL translate F or GL translate D with three arguments, X, Y, and Z. And you can tell very well that these X, Y, and Z would be those translation vectors, the components of the translation vector. This function multiplies the current matrix by a matrix that moves or translates an object by the given X, Y, and Z values, or moves the local coordinate system by the same amounts. Figure 5 that we are going to see shortly, that shows the effect of GL translate. The illustration that you have in your front right now is that of translating an object. So we can think of the object being translated in our grand fixed coordinate system, or we can think of the local coordinate system associated with our object getting translated along the side. So having specified the translation along x-axis, along y-axis, and along z-axis, if we call GL translate function, this is going to establish the translated object transformation. Note that using 0.0, 0.0, 0.0, all three 0 values as the argument for GL translate is the identity operation. That is, it is going to have no effect on any object or its local coordinate system. Next we are going to take up rotate. Void GL rotate F or void GL rotate D using arguments angle, X, Y, and Z, multiplies the current matrix by a matrix that rotates an object or the local coordinate system for that matter in a counterclockwise direction about the ray from the origin through the point X, Y, Z. The angle parameter specifies the angle of rotation in degrees. The function has been built quite generically, where we can specify the angle of rotation and we can also specify what axis of rotation should be used. The axis of rotation is determined by a ray that is drawn from the origin and reaching or passing through the point specified by the three coordinates X, Y, and Z. So a ray from origin to the point X, Y, Z, that would become our axis of rotation, and the angle of rotation would be specified by the angle argument, and then the rotation would be performed around that specified axis with the given angle in the counterclockwise direction. The effect of GL rotate F 45.0, 0.0, 0.0, 1.0, which is a rotation of 45 degrees about the z-axis, is shown in the next figure. Please note how we have specified rotation about z-axis. The angle has been specified, and the three coordinates X, Y, and Z, X and Y of these being zeros, and Z has been specified to be 1. That automatically would be giving us a point on the z-axis. Therefore, the ray from origin to this point would be along the z-axis, and automatically we are going to have rotation performed around z-axis. So you can see in the figure how we have rotated our object, and if we are associating some local coordinate system with it, that too would have been rotated along with it. Note that an object that lies farther from the axis of rotation is more dramatically rotated. That means it has a larger orbit of rotation than an object drawn near the axis. Also, if the angle argument is 0, the GL rotate command has no effect. This we have seen in our earlier example as well, when we said that okay, if we are going to translate our object first and then rotate, having translated the object, we would have moved it away from the origin, from our point of reference which we are going to use for rotation. So having done that, we are going to have our object moving along a trajectory which is going to be visible as kind of part of an orbit. So if we rotate it while it was on the origin, definitely we only had change of orientation of the object. Displacement was definitely not there. So farther away we move from our point of reference for rotation, the larger would be our orbit that we are going to traverse while rotating an object. Next is the scale. Void GL scale f or d takes arguments x, y and z, multiplies the current matrix by a matrix that stretches, shrinks or reflects an object along the axes. Each x, y and z coordinate of every point in the object is multiplied by the corresponding argument x, y or z. The very idea that we have established when in scaling, that would be practically implemented over here. We would be specifying the x, y and z scaling factors, and these factors would be used in order to transform each and every point of our object. All the vertices would go through the same process. Making use of the same scaling factors, we would be scaling all the vertices and then coming up with a transformed set of vertices which would be used to redraw typically our object. With the local coordinate system approach, the local coordinate axes are stretched, shrunk or reflected by the x, y and z factors, and the associated object is transformed with them. Figure 7 shows the effect of GL scale f 2.0 minus 0.5 1.0. Please consider what arguments are being specified with GL scale f. The first one, which is for x scaling factor is 2.0, y is being specified as minus 0.5. 0.5 we can understand. What would this minus have? Think about it. And then z is specified as 1.0. So no change in the z. What do we see? Scaling and reflecting an object. That's what we get. And now you can reckon what that minus was doing over there. So in terms of y, we were specifying minus 0.5 as the scaling factor for y, and that is what has resulted the height being halved and also being reflected. The reflection is towards the minus y part. GL scale is the only one of the 3 modeling transformations that changes the apparent size of an object. Scaling with values greater than 1 stretches an object, and using values less than 1 shrinks them. Scaling with a minus 1.0 value reflects an object across the axis. So the very idea that we have been talking about, scaling can be used for reflection purposes as well. So जहाँ कहीं आपको as it is object की reflection required है, size में कोई change desired नहीं है, मगर सिर्फ आप उसको reflect करवाना चाहते हैं with respect to that axis, उस axis की value जो है उसको 1 ही रहने दीजिए मगर माइनस कर दीजिए. सो हमने -1 अगर स्पेसिफाई कर दिया फॉर y, so we're going to have reflection with respect to y axis of the object achieved as a result of that scaling. The identity values for scaling are 1.0, 1.0, 1.0. In general, we should limit GL scale to cases where necessary. Using GL scale decreases the performance of lighting calculations because the normal vectors have to be renormalized after this transformation. So we have to be careful while making use of GL scale. So wherever we can minimize the use of it, we must. Because what happens is that this causes some hampering in our efficiency. Calculations have to be performed again because our lighting is pretty sensitive to the dimensions and sizes of our objects. So if the size of the object changes, definitely that is going to have an impact on calculation of lighting on it. And of course for that the surface normal or the vertex normal at times would also be an important aspect. So those will have to be computed again whenever we perform such scaling. A scale value of 0 collapses all object coordinates along that axis to 0. It's usually not a good idea to do this because such an operation cannot be undone. Although जिस तरह से हमने अभी आइडेंटिटी मैट्रिक्स की बात की है स्केलिंग के लिए, वैल्यूज 1.0, 1.0, 1.0 हमने स्पेसिफाई कर रखी हैं, दैट्स नॉट गोइंग टू हैव एनी चेंज इन द स्केलिंग, साइज के अंदर कोई भी चेंज नहीं आएगा हमारे ऑब्जेक्ट के. लेकिन अगर हम किसी को फैक्टर 0 दे दें, दैट मीन्स जब 0 स्केलिंग फैक्टर इस्तेमाल होगा तो उस कोऑर्डिनेट की वैल्यू जो है उसको हम ड्रैग करके ला रहे होंगे 0 पे. दैट वुड रिजल्ट इन गेटिंग दैट वैल्यू डाउन टू 0 which was non-zero earlier on. But having performed this kind of scaling will not be able to revert it. देखिए अगर आपने किसी ऑब्जेक्ट का साइज हाफ कर दिया, आपने क्यूब बनाया और फिर इस क्यूब को इन ऑल 3 एक्सिस और कोऑर्डिनेट्स की टर्म्स में x, y और z की टर्म्स में उसको आपने हाफ कर दिया, आपने 0.5, 0.5, 0.5 स्पेसिफाई कर दिया स्केलिंग फैक्टर्स. फाइन, you've gotten it to the half. Now you want it to go back to its original size. You can do the scaling on this scaled object, the cube, using 2.0, 2.0 and 2.0 as the x, y and z scaling factors. You have doubled it again, you got the original picture back. लेकिन अगर किसी भी एक कोऑर्डिनेट को 0 पे ले आए, you would never know what it was originally. So उसको revert करना possible नहीं होगा. So therefore, if required, this must be used with extra caution and care. Sometimes collapsing coordinates does make sense. However, the calculation of shadows on a planar surface is a typical application of this. In general, if a coordinate system is to be collapsed, the projection matrix should be used. Now we are going to take a look at a modeling transformation code example. Next example is a portion of a program that renders a triangle 4 times, as is shown in the next figure. These are the 4 transformed triangles. A solid wireframe triangle is drawn with no modeling transformation. Then the same triangle is drawn again, but with a dashed line stipple and translated. A triangle is drawn with a long dashed line stipple with its height, which is y-axis, halved, and its width, x-axis, increased by 50%. Then a rotated triangle made of dotted lines is drawn. That's the figure that illustrates what we are talking about. The original triangle is the solid one. Then we have stippled line triangle towards left of it. And then the third one, which was halved in height and was stretched in x-axis direction, that is drawn with longer stipple line. And then a dotted line triangle, which is after rotation. So that's what comprises our 4 triangles that we're going to draw using this example. We start by GL load identity, GL color 3F 1.0, 1.0, 1.0, draw triangle, GL enable GL line stipple, GL line stipple 1, F0, F0, GL load identity, GL translate F using arguments minus 20.0, 0.0, 0.0, draw triangle, GL line stipple 1, F00, F, GL load identity, GL scale F 1.5, 0.5, 1.0. Notice the 1.5 and the 0.5, that would be altering the width and the height. Draw triangle, GL line stipple 1, 8888, GL load identity, GL rotate F 90.0, 0.0, 0.0, 1.0, 90.0 being the angle and 001 giving the point through which the ray starting from origin would pass and would form our axis of rotation, which in this case again would be the z-axis. Draw triangle, GL disable GL line stipple. Note the use of GL load identity to isolate the effects of modeling transformations. Initializing the matrix values prevents successive transformations from having a cumulative effect. We've talked about it earlier. हमारी जो transformation current है, if that is what we want to have effect, we better load GL identity matrix and then perform our transformation. Even though using GL load identity repeatedly has the desired effect, it may be inefficient because we may have to re-specify viewing or modeling transformations. Also note that sometimes programmers who want a continuously rotating object attempt to achieve this by repeatedly applying a rotation matrix that has small values. The problem with this technique is that because of round-off errors, the product of thousands of tiny rotations gradually drifts away from the value that we really want. It might even become something that isn't a rotation. So instead of using this, we can use another technique, which is to increment the angle and issue a new rotation command with the new angle at each update step. So the idea is that rather than successively providing those rotation commands repeatedly, we can do this by repeatedly issuing the rotation command from scratch using incremented angle value, and that is going to ensure that our reference would be sane and we are going to get healthy results. Now let's talk about some viewing transformations as well. We are done with that modeling part. A viewing transformation changes the position and orientation of the viewpoint. If we recall the camera analogy, the viewing transformation positions the camera tripod pointing the camera towards the model. Just as we move the camera to some position and rotate it until it points in the desired direction, viewing transformations are generally composed of translations and rotations. To achieve a certain scene composition in the final image, we can either move the camera or move all the objects in the opposite direction. Thus, a modeling transformation that rotates an object counterclockwise is equivalent to a viewing transformation that rotates the camera clockwise. Finally, the viewing transformation commands must be called before any modeling transformations are performed, so that the modeling transformations take effect on the object first. We can manufacture a viewing transformation in any of several ways, as described next. We can also choose to use the default location and orientation of the viewpoint, which is at the origin, looking down the negative z-axis. The one way of doing it would be that modeling transformation commands can be used. GL translate is already something that we have covered. GL rotate is also something that we know about. So if this is what we are going to do, making use of our viewing transformations, we are going to translate and rotate the object, we can use GL translate and GL rotate, F or D. We can think of the effect of these transformations as moving the camera position or as moving all the objects in the world relative to a stationary camera. Then we can use the utility library routine GLU lookat to define a line of sight. This routine encapsulates a series of rotation and translation commands. So effectively it does what we want to do. Create your own utility routine that encapsulates rotations and translations. This is yet another option for you. Some applications might require custom routines that allow to specify the viewing transformation in a convenient way. For example, we might want to specify the roll, pitch, and heading rotation angles for a plane in flight, or to specify a transformation for a camera that's orbiting around an object. Now we can quickly take a look at using the GL translate and GL rotate method. Of course, this method is in spirit analogous to what we are doing in the thinking process. So if we have thought our viewing right, we have connected the dots, we know exactly what translation and rotation would achieve the end result that we want. Because ultimately है तो वही कि हम scene के ऊपर अपना view जो है उसको इस तरह से पॉइज करना चाहते हैं कि जो हमारी रिक्वायरमेंट है वो नज़र आ सके. सो जिस तरह से हम कैमरे को मूव करते हैं, फ्रॉम ट्रांसलेट करते हैं, उसको रोटेट करते हैं और अपने ऑब्जेक्ट ऑफ इंटरेस्ट के ऊपर पॉइंट करते हैं, बिल्कुल वही काम हमें यहाँ पर भी करना है. सो वही व्यूइंग ट्रांसफॉर्मेशंस हम खुद से अचीव कर सकते हैं, मेकिंग यूज ऑफ दीज टू transformations. So if we use the default values in which we say that our viewpoint is considered to be at the origin, और हम अपने ऑब्जेक्ट को भी अगर प्रिज्यूम कर रहे हैं कि वो ऑरिजिन पर ही है, तो जो इलस्ट्रेशन आप इस वक्त देख रहे हैं, दैट वुड बी द सिनेरियो दैट आवर ऑब्जेक्ट एंड आवर व्यू पॉइंट वुड बी एट द ऑरिजिन. सो गिवन दिस काइंड ऑफ अ सिचुएशन वेयर आवर व्यू पॉइंट and our object are at the origin, we would be interested in separating the two. So in the simplest case, we can move the viewpoint backward away from the objects, or what we can do is we can move the objects away from that viewpoint. So this figure shows what we would be achieving as the end result. So we can separate the viewpoint and the object, and this can be achieved making use of one of the two techniques, either moving the viewpoint away or moving the objects away. Of course, these movements would be in opposite directions. Now suppose that we want to view the objects from the side. Now should we issue a rotate command first or after the translate command? If we are thinking in terms of a grand fixed coordinate system, first let's imagine that both the object and the camera or our viewpoint are at the origin. We could rotate the object first and then move it away from the camera so that the desired side is visible. There is one way of doing it. That you rotate the object, its orientation changes, you take it away so that it is now visible, and the new side, the different angle that we wanted to show, that would now be visible. Since we know that with the fixed coordinate system approach, commands have to be issued in the opposite order in which they should take effect, we know that we need to write the translate command first in our code and then follow it with the rotate command. Now let's use the local coordinate system approach. In this case, think about moving the object and its local coordinate system away from the origin. Then the rotate command is carried out using the now translated coordinate system. With this approach, commands are issued in the order in which they are applied. So once again, the translate command comes first. Thus, the sequence of transformation commands to produce the desired result would be GL translate 0.0, 0.0, minus 5.0, GL rotate F 90.0, 0.0, 1.0, 0.0. If we are having trouble keeping track of the effect of successive matrix multiplications, then try using both the fixed and local coordinate system approaches and see whether one makes more sense or the other. Please also note that with the fixed coordinate system, rotations always occur about the grand origin, whereas with the local coordinate system, rotations occur about the origin of the local system. We might also try using the GLU look at utility routine. So folks, today we have talked about the modeling and viewing transformations, and we have seen how we can compare the two processes and make use of some real life analogies of photography and combine them with the idea of implementation using OpenGL. There are multiple ways of achieving the same results or same effects. We have seen many of those ways, and we have tried to develop a feel for the thinking process that actually drives this implementation. We have stressed the need of thinking the correct order of transformations first and then applying them. We have also worked out the differences between making use of the grand fixed coordinate systems as well as the local coordinate systems of objects in order to come up with appropriate order of transformations. I hope this discussion is going to be fruitful for you, and you'll be able to make use of these to come up with your own ideas and try to master them in order to become an efficient OpenGL programmer. So folks, let's call it a day over here. We have talked about the model view matrix, and we have talked about the combination of modeling and viewing transformations together and we have also developed a feel for the order in which these transformations need to be performed before we can get the desired results. So this discussion can always continue, but of course we have to stop somewhere. So the rest of the things we'll be trying to provide you with more information and more material, but that you'll have to go on your own, and you would be discovering some more fascinating and interesting facts about implementation of modeling and viewing techniques using OpenGL. Next time we'll see you again inshallah. Tab tak ijazat dijiye. Allah Hafiz.